Hello students, welcome to the session. Today's topic for the session is Introduction to the Limit. So we will see the basic definition of the limit and how to calculate the questions of limit. So let's start the class. See, in this you will observe expressions like this: limit extending to a, is from the x-axis point of view. Okay, in the graph I will also explain. This limit extending to a means you are approaching to a number a on the domain that is on the x-axis, and f of x means your function that you will get from your y-axis. Okay, and this is the limiting value. This is your limiting value of function at x is equals to a, at x equals to a. See, this information you should know. Limit extending to a means you are approaching to a. See, if you are on x-axis, this limit extending to a means, see, it is your, if it is your x-axis, that means that you are approaching to a from either of the side, either from this side or this side. Okay, if a is your number, any number 5, 4, 6, 3, 2, 1, any number. So there are two possibilities that you approach from here, or you approach from this side, or you approach from this side. If you are approaching to a, this will be, if you are approaching to a from this side, this will be your left hand. In terms of limit, it will be your left hand limit. And if you are approaching from the right side, this side will be called your right hand limit, RHL, right hand limit. Okay, so this is the point behind the approaching limit extending to a. Limit extending to a means if you are approaching to a on the x-axis, either from the left side or the right side. If you are approaching from the left side, it will be called left hand, and if you are approaching from the right side, it will be called right hand. And in terms of limit, it will be left hand limit, LHL and RHL. And this is now your function. Okay, so now if you are moving on the x-axis, that is you are tending towards a, from this side. At that time your function value will also be changing. Okay, your function value will also be changing like this. In it, corresponding to different values of x, your function values will also get changed from this side. Okay, so this means as you are moving on the x-axis also, your values of x are changing as well. Your values of the function will also get changed. Okay, so we will discuss on the graph also. And this is your f at a, that function value at a point. Okay, that function value at a point. Let us say it is your a. At a, your function value will be a comma f a. In ordered pair, we can write list at, see, in ordered pair we write like this, x comma y. Similarly, here your input is a and your output is f8. That is your function y is equals to fx. Okay, so let's understand the graph. See, if it is your graph like this, let's get a better understanding. So if your a point is here, see, not a, let's suppose if you are taking your 5 point is here and you have a graph like this. Okay, now let's say we have to deal, see, if your x tending to 5 is here like this, that means you have to take the neighborhood points of 5. You have to consider the limit in the neighborhood points of 5. Neighborhood means very near to 5. Okay, so see, it is saying that you are approaching to 5 x-axis. That means you can approach from here also -1, 0, 1 also. This is also the possibility, but we should take our approaching from the neighborhoods. Okay, so very near to 5, just like this bracket. This is the neighborhood. This is denoting the neighborhood of 5. So we have to approach 5 in this way only. Now, if you are approaching from right side, it will be represented like this, and if you are approaching from left side, it will be represented like this. Now, similarly, at this point, at this point, at this point on x-axis, you will get your some y value also. Okay, let us say this is your function f of x. Okay, at this point, you will get your some function. At this point also, you will get some value of your function. Okay, similarly at this point also you will get, putting the x, you will get some value of the function. Here also you will get some value of the function also, and at 5 also, you will get that function value, and this will be called as f of 5. So corresponding to every value of x, you will get your functional value. And at the point where we are checking the limits extending to 5, we will get our limiting value, that is your f at that value. Okay, this is the basic introduction of limit through the graph. So main thing is that if you are approaching from the either from the left side or right side on the x-axis, your value gets also changed with respect to the graph also, that is from the y-axis point of view. See, in y-axis point of view, we will mark the graph like this. At this point it is like this. At this point you will get the value like this, and at 5 you will be having that value like this. Okay, this is your graph representation. Similarly for this value also, so for every corresponding neighborhood values of 5, you will get your functional value. So this is the graphical representation of the limit. So basically what we should know, limit extending to a, f at x is equals to f at a. This is the notation for a limit. Okay, so this is the function, this is the extending to a, whatever point is there, we are approaching to that point, the functional value should be given there, and it is your limiting value f at a. So basically, if we say that limit exists, if we say that our limit exists or doesn't exist, okay, so it depends all upon the left hand limit and right hand limit. If they are equal, then our limits exist. If they are not equal, our limit does not exist. Okay, so let's see an example. See, through the graph only we will get better understanding. If we have, this is our x-axis, 0, 1, 2, 3. This is our x, this is our x dash, this is our y. Okay, so this is our 1, this is our 2, this is our 3. So let's make a graph. Let us make a graph passing through 1, 2, 3, then goes like up to 3, then like this. Okay, now if they ask to find the limit at x tending to 3, f at x, see the graph, see whatever on the portion of the y-axis, we always represent like this, y is equals to f of x. So it will be called your y is equals to f of x. Clear? Now, what they are asking limit extending to 3 f at x. Okay, that means we have to approach from both the side. Let's check for the left hand limit. Left hand limit is denoted by limit extending to 3 minus f at x. So let's check the value at the left hand side of the 3. So if you are approaching from the left side of the 3, at that time your functional value is your 1. Your functional value is your 1. Functional value is your 1. But if you are approaching from the at 3 from the right side, that means from here, like this. At that time, not at 3. Okay. So there is a difference. We are always saying that tending to 3. That doesn't mean that you are at x equals to 3. You cannot consider at x equals to 3. So it, we are saying that we are approaching to 3 from the right side, and from the right side, we have to see the functional value. So we have to see the functional value. The functional value in this case is the functional value in this case is 3. Okay, so we are getting our value 3. So our left hand limit and this is our right hand limit, they are not equal. Left hand limit is not equals to right hand limit. So that means that our limit does not exist at x is equals to 3, because your left hand limit value is your 1 and the right hand limit value is your 3. So they are not equal. So if they ask, find the limit at x equals to 0, at x equals to 0. So we will break into left hand limit extending to 0 minus and limit extending to 0 plus at f of x and f of x. Okay. So limit extending to 0 minus means here it is your 0 and you are approaching from this side. So at this point, your functional value is 1. Your functional value is 1. So limit extending to 0 minus, you are getting a function as 1. And if we put a limit here, we will get our constant function. We are getting our limiting value as 1. We are getting our limiting value as 1. Similarly, if we approach 0 from the right side, if we are approaching from 0 from the right side, what we are getting our function, first identify the function, we are getting our function as 1. So we will put limit extending to 0 plus fx at 1. Fx value is 1 because it is a constant function. Okay. So clearly extending to 0 plus, at applying the limit on constant function, we get the same value. Okay, we get the same value, that is your 1. That is your 1. So your left hand limit and your right hand limit both are equal. That means the function, the limit exists. The limit of this function exists. Clear? So the limit of this value of this function exists, and what is the limit? The limit will be what? At 0. At 0, what is the function value? At 0, if we put the function, if we put the 0, what we will get? We will get our functional value or limiting value at as 1. So your left hand limit is also exists, right hand limit also exists, and limit extending to 0 at f of 0, you are getting what? 1. At f of 0, you are getting your value as 1. Clear? So this is the graphical representation. In this way, we can find function which has limit can exist and limit cannot exist. So let's do some numericals based on the direct substitution approach. Direct substitution method. So direct substitution method means if limit extending to a f of x, we have to just put the value x at x equals to a, we will get our answer at f of a. Clear? So this means what? The condition is that if we are substituting, if we are substituting x is equal to a, then our function f of a should be defined. Okay, should be should be defined. Okay, it should be defined. Defined means we should not get our undefined form or indeterminate form. Okay, indeterminate form means we should not get like 0 by 0, 1 by 0, okay, infinity by infinity. We should not get this type of expression. We should get, on putting the value, we should get our function as a well defined. So let's see one example. If it is given that limit extending to 3 x plus 3, we have to find the limit of this expression. So just if we put our value x equals to 3, we will get our 3 plus 3 is equals to 6. This is the limit of this function. Here, this is the limit of this function. If they ask you limit extending to 5 minus x. So if direct substitution method, what it say, it is your f of x. Okay, so let's do a detailed method. So it, let your f of x is equals to 5 minus x and u of x is equals to 2. Just putting the value here, f of 2, calculate the value, f minus 2, you will get your 3. That means the limit of this function at x minus 2 is equals to 3. Okay, so this is the one method, direct substitution method, but always remember that it extending to doesn't imply that you can, your x is equals to 2. It is tending to 2. Tending to 2 means it is nearby 2. From here side it will be 1.99999 something type, and from this side it is 2.00001 something this type. Okay, very near. Okay, and if we read on the graph, it is, if it is here, your x value is here, your y value will be according to the f of 2. Okay, it is approaching to f of 2, and from left side and from right side it will be approaching to f of 2, f of 2. So on x-axis we will have 2, on and on the graph we will have f of 2, f of 2. If we are approaching to x, if we are approaching to 2 on x-axis, it is extending to 2, and if we are approaching on the graph, it will be approaching to f at 2. So we are getting the value nearby f of 2 at the point where we are calculating our limit. So we should be very much clear. So extending to 2 means we are getting the limit f I minus 2 is equals to 3. That 3 means on the graph, clear? Okay, so that's all for today. I hope you understood the topic. If you have any doubt, you can contact me through Urban Pro Profile app. Till then, revise, practice. Let's meet in the next session. Thank you.